So thank you for having me here today, this morning. And yeah, so in this presentation, I think it follows very nicely from the previous one. I will talk a bit about the developments on data assimilation that we have been working on at ECMWF to build a new emission inversion system. And I will start by saying something about the project which has funded most of the work that has been done so far, which is the COCO2 project. And the COCO2 project will lead to this Copernicus monitoring and verification system for CO2 anthropogenic emissions that will be an operational service, the global component of which will be led by ECMWF in a few years. And the idea here is that we're gonna develop the global component of the system, in which, as you see in this slide, we basically take in real time observations of atmospheric CO2, and we combine this information with some prior information which come mostly from emission inventories, and we combine them. And basically, in order to kind of have a system that can monitor and verify the emissions, global, especially anthropogenic CO2 emissions, so that we can basically have a service that can inform policymakers and people having to take the decision, especially in view of keeping track of the progress for the implementation of the Paris Agreement. So there are, I would say, three main developments that we have been working on at the center. So as a premise, the ECMWF already runs an atmospheric composition version of the IFS, of the global integrating forecasting system. And usually the atmospheric composition version is referred to as IFS compo in the literature or in the documentation. And we run it for both reactive, we assimilate in this model both reactive species, so CO, NO2, ozone, but also greenhouse gases, which are more the focus of this presentation, like CO2 and methane. And so there are three areas in which we are developing the system further. One, of course, so currently basically the data assimilation scheme that we are using for the composition species is only basically only optimizing the concentrations. And so this is, of course, not enough if one wants to have a system. I mean, the atmospheric composition is mostly more constrained by the boundary condition, by the emission model, the initial conditions. So having a system that manages to optimize the emissions is, of course, necessary. The other big thing that we have done is to extend the ensemble approach that is already used in the NWP to the atmospheric composition. So basically developing an ensemble of data simulation for GHG. And then the last bit, which is still a bit under development, is working on the duration of the assimilation window, because currently we have 12 hours, so we can also use a 24 hours assimilation window, but this is still basically something that comes from the NWP system, and for long-lived species like CO2 is probably suboptimal, and we need a much longer window, and so that is also some work that we are doing. So how does the new emission inversion system works? Basically, we have added, so as I said, currently we're only, the IFS compo only, the assimilation scheme in the IFS compo only assimilates, only optimizes the concentrations. And the idea here is that we can add a 2D emission scaling factor field, which is species and sector dependent. And this is optimized jointly with the atmospheric composition concentrations and the meteorology. And this is, of course, like a nice advantage of developing this at ECMWF, because we already have kind of infrastructure in place to optimize these two things, and we can add also the optimization of the emissions inside. And so at the moment we are doing this on a window which is 12 to 24 hours long. And we only assimilate satellite observations, which mostly means total or partial column retrievals. And the resolutions used are 25 kilometers for the model and 80 kilometers for the increments of the scaling factor optimization. Of course, here it's quite important to define the covariance matrix for the prior emission, so this BP. And at the moment, we are using a very simple one, but there is also another project which ECMWF is involved with, which is a Corso project in which will basically develop a better covariance matrix, which will also take into account some, for example, cross-species correlations between CO2 and other gases. And this is just a schematic representation of how the system works at the moment, which is basically optimizing the emission and the concentrations jointly in each short window. And the second bit, as I said, was the data assimilation development. The ensemble of data assimilation, the extension of the ensemble of data assimilation to atmospheric composition species. So while the EDA, which is already operational for the NWP, has basically two purposes. One is to provide an estimate of the posterior uncertainty, so to produce an ensemble of analysis. And the other one is to update the background covariance matrix with some flow-dependent information. And in order to do this, at ECMWF, we perturb three elements in the system. One is the model error through the perturbation of the physical tendencies, the observation error, and we perturb the observations, and then we perturb also the sea surface temperature. And the idea here is that as in the EDA for atmospheric compositions, we also perturb the initial emissions. And then basically the way we perturb the initial emission is we basically use the prior emission certainty covariance matrix BP. And at the moment, as I said, this is a very kind of simple matrix. So we just have a uniform constant standard deviation, which we use to perturb our emissions. And there is no correlation involved. And we use a log normal distribution basically because we want to preserve the sign of the emissions. We don't want to have negative emissions. So we use a log normal distribution to do these perturbations, to sample the perturbations. Okay. Just a bit of a comment. So the EDA has kind of allowed us to develop a way to kind of validate or at least check that the system is working, and also to do some tests in a kind of a control environment. So we have developed this EDA, which we are using for some experiments and simulations. We have developed this OSSI, observing system simulation experiments, which is based on the EDA. So what we do here is that basically we consider the control member as our nature run, and in which we assimilate the observations as they are, and we use the prior emissions as they come from the inventory. But then from the control member, from the first guess, basically we get some synthetic observations which we perturbed, and then we use in the ensemble. And so the ensemble will assimilate synthetic observations coming from the control member plus the and then you will use the emissions as they are in the inventory, and then plus perturbations. And so in this way, basically, we have more control on what we are doing, and we can do some checks, and I'll show some very early results in a couple of slides. And the other bit that we are developing, and this is still under development, but it's nice that maybe we talk about it. So it's basically, this is the idea of extending our 4D window for GHG species. So as I said before, 12 hours, 24 hours is not enough for species like CO2, which stays in the atmosphere for very long. So using only the observations of the last 12 to 24 hours is not enough. So what we do is we we have come up with this idea of having a longer window for those gases. So everything I've talked so far has basically only has been about this window here. So the a window in which basically we have some observations to assimilate, and we have a tangent and a linear adjoint models. But the idea here is that since we have an EDA, we can use the EDA, we can use the ensemble to build an approximation of a transport Jacobian for the past windows, so for the past time, basically relating the concentrations at a certain time with the emissions at the previous times. And then using we can basically then back optimize the emissions in previous windows using this Jacobian, starting from the windows we are already at. And of course, then we can also run an ensemble in the future and producing a posterior distribution, which is also based on the ensemble. And yeah, here's some, just to show you some early results. So we have run this, we are using the OSI system to kind of test that the system is working. So here we have run an experiment, and we have tried to, we have plotted here the uncertainty reduction, which is a common metrics in, I would say, in inversion, in the inversion community, which is basically defined as 1 minus the difference between the posterior standard deviation and the prior standard deviation. So in this case, they're both, they come from the ensemble that we are running. And so in this case, we have run a 50 members ensemble, and our prior emission standard deviation is 100%. And this is for methane, not for CO2. And the reason is that, as I said, 12 hours is not really great for CO2, and it works a bit better for methane because it's a different gas and it behaves in a different way. And so here you see that the emission reduction goes up to 50% in some areas, and it tracks quite well the location where we have most of the observations, the subtle observation that we're using. And if I go on one slide, you can see also that also visually, if you compare the prior and the posterior ensemble distributions, you do see a reduction in the spread, a reduction in the uncertainty. So here the prior is in purple and the posterior is in yellow, and you can also see the value of the standard deviation of the prior and the posterior for a few locations where the signal is particularly strong. Okay, so this was my last slide. So just as a summary of the work we are doing at ECMWF to set up a new emission inversion system. So we're developing basically the global component of this new operational service that will, which will be under Copernicus and will act as a monitoring and verification service for anthropogenic CO2 emissions. What we have done to do this is basically we have expanded our 4D-VAR algorithm so that also a two-dimensional emission scaling factor fields can be optimized jointly with the concentration and the meteorology. And we also have extended the EDA approach to GHG species. And in here, we include the perturbation to the initial emissions. We also have developed an OSI framework in which we use the control member as a need to run, and then we extract from it some synthetic observation that the ensemble, that are simulated in the ensemble members. And we are working on an extended 4D-VAR window for GHG so that we can improve the constraint for long-lived species like CO2. And yeah, and we have run some early results, and I hope we will be able to show much more in Bologna in October because we have submitted a couple of abstracts there. So thank you for your attention.
Thank you very much, Luca, for this nice overview. And yeah, there's already one question in the Yopad by Shivaji Patel. I'm not sure if I understand it correctly. I think the question is about the length of the assimilation window, so like 12 or 24 hours. And also the question is, what would be the impact of taking like shorter windows of 6 hours? So did you try this or?
We haven't tried, so we tried 12 and 24 hours. We haven't tried shorter windows. I can't imagine why it would improve things. Well, it's very much species dependent. Like if you have this is for GHG, so especially CO2 needs a longer window. I would say days, weeks. Then we are also running this system for other species. For example, NO2, and these gases are much more reactive, and they tend to, once they emit, they decay very quickly. So you don't need a long window for those. And yeah, so I think here is more a matter of extending the window more than like reducing it. If I have understood the question. Yeah.
Okay, thanks. So then I have another question. I'm not sure if other people want to ask questions. Please use the OPED. So we all know that in data assimilation, the magic comes from the covariance matrix.
Yeah.
So it helps us to distribute the information. And you said that you want to use a more sophisticated emission uncertainty covariance matrix. And you also referred to like cross covariances between different species. And I was wondering, so how do they behave? What do they depend on? Can you comment on that?
Yeah, I'm not a big expert on this. What I know, for example, though, is that CO, carbon monoxide, is correlated quite well with CO2 emissions. So, and it's easier to detect from observations. So the idea here is that detecting, being able to, if we assimilate, if we know that there is a plume of CO somewhere, we probably know there is also some CO2. Of course, then the details are important, and trying to estimate one from the other is not trivial. And that's why we had this project that will basically entirely spend time on trying to find out what's the best, what are the best options here. But the idea, yes, is some species that are not CO2 are easier to constrain and are easier to observe. And so if we find a good correlation between them and CO2, we can basically use those to further constrain the system, on top of assimilating CO2 observations, which we will always do.
Sounds very promising. So I'm looking forward to see more results on that. And yeah, so there are no more questions in the OPED. If there are some questions coming up, please ask them. Luca can still answer them in written form. And yeah, I want to thank Luca again for the nice presentation.
Yeah, thank you.